Hi, my name is Celeste Freilich. I'm the Chief Data Scientist and Senior Principal Engineer of McAfee. Today, as a summary of the agenda you see on the slide, I hope the audience will walk away with old and new ideas about AI reliability and begin to put into place some key monitors in DevOps and MLOps. These monitors are the baseline, the foundation of AI reliability, and I will give you some proposed mathematical models for AI reliability that will end up with the population of an important AI reliability term I want to introduce today called mean time to decay, MTDD. So let's walk you through how to get there. First of all, to start at the beginning, there are three words that have become very prevalent when speaking about AI. The first one is robustness, and it's got a whole bunch of synonyms. Sorry, I must be thinking about breakfast. Hardiness, lustiness, strength, soundness, health, toughness. Typically, it has referred to the ability of a computer system to cope with errors during execution and erroneous input. We can extend that concept to AI. How effective is your algorithm while being tested on a new, independent, but similar data set? Now, this property is also known as algorithmic stability. And in fact, in many cases, we minimize the error rate, such as mean squared error, and maximize peak signal to noise ratio to ensure a stable algorithm. So that's robustness. The second word is resilience. Resilience means as inputs ebb and flow, does the model still perform the same way? It also implies toughness. I like to think I'm very resilient, and the ability to adapt to risks and continued operation of core business functions despite challenges. Now, the last term is trustworthiness, and trustworthiness has been used by the Boy Scouts for many years, and now it is embraced by NIST, the National Institute of Standards and Technology in the United States, and ISO in their new AI documents. But these three words are critical to describe what we expect out of AI, but we can use it to form the basis of AI reliability. Now, AI reliability is the intended performance over time. Performance can be accuracy, it can be false positives, AUC, or whatever your business need states for what's important for you, for the business, for the customer. Our three common words combine to support AI reliability, and they ensure reliability can be measured via the monitors each word represents. And AI reliability can answer the question of how stable is your monitor, or how stable is your algorithm? Can your model, does it have the ability to adapt to risks? And can you adopt AI without fear? And that's where bias and AML, adversarial machine learning, comes into play, and ethics. So these three words combine to form AI reliability, and it begs the question of, most importantly, how long will my model last in the field? So additional reasons for AI are numerous that I'm listing here. Just as your car or your airplane's reliability provides you a sense of security and certain expectations, reliability can be critical to us as customers, but the company CEO is concerned about growth, he's concerned about competition, and he's concerned about customer satisfaction. Well, suffice it to say that as a revitalized technology from the discovery of AI by John McCarthy in 1956, and one that currently manages most facets of our digital life. It's timely. No, I'd say it's probably required right now to assess AI's reliability. Now, AI reliability mathematics, they've been around for a long time. They're applied to everything from our cars, our refrigerators, our computer chips and phones, to the very clothes we wear. It is the manufacturer's prediction of how long the product will perform, its intended function. It's the best by date of your milk, to the recommended cleaning frequency of your teeth by your dentist. It's graphically typically shown as a bathtub curve. It starts with infant mortality with a decreasing failure rate, and this is known as quality. This is the great car that you bought and it works just great. Then there's a happy place known as a normal life or useful life, where you have a low or constant failure rate. And then pretty soon, you have increasing calls to the car repairman, and you have an end of life wear out with an increasing failure rate, and your milk starts to sour and things like that. So the general definition of reliability embraces mathematical models that build this bathtub curve up over years and years. So let's take, now that's normally for hardware, but let's take a look at software. Now, software reliability has also evolved over years, and let me quote, because I think it's an incredible quote. It says, "It's an estimate of the level of business risk and the likelihood of potential application failures and defects the application will experience when placed in operation." I think that's a great definition of software reliability. We're very familiar with the fact that it can utilize errors detected at each stage of development. It's even using neural networks and other AI tools to assess and predict failures. Software reliability still addresses those core items such as functional and structural quality, typically in the SQA organization, as well as the old standby that I mentioned, that errors detected at each stage. They also use combinatorial test design to identify the optimum number of tests needed for the coverage they desire. Well, Microsoft has done a great job at creating some reliability measurements, such as the Office Customer Experience Improvement Program, or CEIP, and Microsoft Reliability Analysis Service, MRAS. You can find details of these acronyms and other Microsoft programs within this paper here. Now, I'm sure you're all familiar with the CISQ software quality model on reliability, but what I want to point out, and what I've highlighted in yellow there, is the fact that they also call out those three important words: so resiliency, stability, or robustness, and all important monitoring. And monitoring is so important to the critical concept of reliability. However, both software and general reliability equations of the bathtub curve have yet to address the reliability of AI. And as I don't think AI reliability fits into either one of them, but we can certainly utilize some of their calculations. And so a new paradigm needs to be considered so we can predict the life of a model in the field. So consider then these questions about reliability. How do you predict reliability of an AI model? How do you utilize robustness, resilience, and trustworthiness? What are the factors or features that drive reliability, and how do they change? And how does AI reliability change over time? Now, To give some guidance to answering these questions, we must look at the entirety of AI development and deployment in the field from soup to nuts. Now, most developers are anxious to create the latest exciting model. I know I am. And as developers and DevOps or development operations has been a mainstay of developing code as well as end-state models for years and years. But DevOps is necessary, but it's not sufficient. AI is more than just software code. It is based on curated data that requires targeted actions built in from the beginning of and during model development. But once also monitored, you also have to consider the deployment of the model in the field with your customers. So implementing monitors at the beginning of, during, and while in the field constitute the typical organizational structure of DevOps and MLOps. And while the picture here on the right is just an example, yours may be more or less delineated or skewed, most likely to DevOps, most are. But what we need to do is monitor design and checks and balances as well as field performance. And now AI is moving from development-centric to consumption-centric activities. And we'll find that just as in DevOps, that with MLOps, there's a 3 to 15% profit margin increase with implementing MLOps, which includes model monitoring there in the lower right. In fact, MLOps market, they believe will be greater than $4 billion by 2025, which is, yikes, only 4 years away. So it's important to consider that you look at both DevOps and MLOps as well as field performance. Now, to review what we've discussed, consider that robustness, resilience, and trustworthiness provide input into monitors that can be implemented in DevOps, MLOps, or in the field. We ensure that there is always a feedback loop, as you see at the top there. And we want to make sure that that feedback loop goes from into DevOps and MLOps to place alerts, revisions, thresholds, or root cause analysis. I've referred to the term monitors throughout the talk thus far. So let's take a look at some of those examples. Now, let's see, I want to make sure you can. There we go. All right. So these next two slides I know are maybe a lot to take in, but what I want to do is just consider suggestions on monitors. And what I've done in these next two slides is just giving you an idea of some of those monitors that can be placed in MLOps, both, or DevOps. Okay, and you should all be familiar with some of these, but what I want to do is make sure that you look at these from a prioritized standpoint. Things such as low-hanging fruit, like skewness, kurtosis, variance for concept drift or data decay, volumes and types. Looking at downsampling, your storage, your caches, looking at your error rates or ROC curves over a set of time. So these in itself can be a good place to start. The second page is additional monitors that you might consider: adversarial machine learning or model hacking, where poisoning or evasion can drive up your false positives or false negatives. Your bias, certainly every one of us have it. We want to make sure that we also consider within not just sampling, measurement, algorithmic, and but also prejudicial In prejudicial, remember, we have societal changes, such as racial unrest in the US. So your bias may become much more sensitive over a period of time. How does your AI model react to that? So you have to keep in mind some of your societal concerns as well. And certainly explainability, where you can explain explainability by design with some of the ALIME, GradCam, and SHAP monitors. And interpretability, which is something that is not very common yet, but it implies that you have UI and UX principles first, user interface principles first. And it enables people to be part of the decision making, and AI explainability helps that quite a bit as well. Certainly anomalies, and for this crowd, cybersecurity obviously is very important, with the number and type of malware, including the exclusive detections, as well as the falses, and the threat families. Have the threat families changed over time? So after you've completed looking at these monitors, and you've selected them, you've baselined them, and you've measured them, now you have a model that has an expected lifetime, noted by the red dot there, until it starts decay, noted here as a solid black line. When retraining occurs, because of the decay, the model is refreshed, as noted from the red arrow, and measured by the business goal. And in this graph, I've selected accuracy, seen on the y-axis. Yours may be different. And the decay causes are highly dependent. The decay causes there in the rectangles, blue, green, pink, and purplish. They're highly dependent on what monitors you have put in place, such as those listed in the last two slides. So they may be single, they may be cumulative causes, they may have different uses of units of measure. So you need to consider each one of those. Now, I know you think that that's probably it. You can go off and do your calculations, but of course we have to have some math. So first of all, we want to consider the calculate the instantaneous decay rate of our model. We want to consider the conditional probability that B will occur given A is known to have occurred. Now, that's just for two causes, but of course you may have, you may have perhaps a couple of dozen causes. We don't know that. It's based on what you've monitored. Your probability calculations will then be converted to a rate. And after you place them into a rate, you can let the change of time approach to zero and obtain the derivative of m of t, denoted by m prime of t divided by r of t in equation 3. And lastly, you'll get an instantaneous failure rate of h sub t. Now, however, it may be more useful for you to consider a single average number or even a cumulative decay rate of the original model. So here I provided that by integrating the instantaneous failure rate over the interval and dividing by the time difference. And the time difference may be different, might be weekly, might be daily, might be monthly, might be time 0 might be when you go live. Time 1 might be 60 days. Time 2 might be 62 days. Time 3 might be 80 days. It really depends. So at this point, when you're calculating your average decay rate, this is all based on the first four equations that I showed you. So by integrating the instantaneous failure rate over the interval and dividing the time difference, you can achieve an ADR, or average decay rate. Now in equation 6, sorry, just checking my notes here. As the monitor changes are measured, you may find that cumulative decay rate is required, and I like this quite a bit. It's a small fraction of a change in a few monitors may be enough to alert that the model has decayed perilously. So this is well documented in the 1986 Challenger explosion disaster, where an O-ring caused a fatal error due to cumulative failures. Unfortunately, there were 8 O-rings, and all had to function at 0.99 or 99%. The system reliability, therefore, was 0.99 to the 8th power, or 0.89, a potential failure rate of 0.11, or about 1 out of 9 instances, and the explosion occurred in the 12th shuttle launch. So that cumulative decay rate is very important. These calculations are based on a general reliability theory. Typically, software checks and balances can be added to cumulative probability equation. Now, also consider whether the change in monitor is independent of others or is dependent on others. Now, what we want to get to is mean time to decay. So the probability distribution function is related to the CDF, or cumulative distribution function, being an integration equation that I haven't shown, but it's in most reliability books, and can be related to the monitor failure rate with equation 7 here. Now, CDF helps to specify the distribution of multivariate random variables, and therefore it's great at reflecting the monitors we have in place. Now, mean time to decay is what we're looking for. Lambda is failure rate, and since instantaneous failure rate, h of t, varies over time, we define a single average number that reflects behavior over a specific interval. Now, MTDD can be reported to analysts. It can be reported to customers, competitors, and investors to demonstrate the robustness, the resilience, and trustworthiness of any AI model you use. See how I link that back to those 3 words? All right, to summarize, defining and implementing your monitors will be the hardest challenge. That's definitely the hardest. The math is simpler. To select the monitors, you can utilize the 2 slides that I provided for you here, or you can review the NIST and ISO documents for added monitor insights in robustness, resilience, and trustworthiness. Identify and improve current monitors in your DevOps, MLOps, and in the field. Make sure that you have a feedback loop, and once monitors are implemented, you can collect the metrics such as the change in units per time, and utilize these monitor metrics within your reliability models. And you can calculate instantaneous, cumulative, average failure rate, and you can culminate in a reportable and very public mean time to decay. Now, while we have enjoyed developing cool new models since AI has resurfaced, it is important for all of us now to consider long-term implications. improve our processes, and set our sights on calculating AI reliability. Thank you very much.